Welcome back to PrepForge. So far we've built up systems, Kafka, RabbitMQ, and SQS. Today we go smaller and sharper, to a data structure that shows up in system design interviews constantly, the Bloom filter. Here's the one-line pitch. A Bloom filter can tell you, using very little memory, whether an element is probably in a set, or definitely not in it. It trades a little accuracy for a huge saving in space. In this video we'll build one from scratch with a running example, insert and look up elements, understand false positives, do the math, look at real code, and see where giants like Cassandra and Google use it. Let's get started. Let's start with the problem. Suppose you run a service with 10 million known bad URLs, and for every web request you need to answer one question: is this URL on the block list? The obvious approach is to store all 10 million in a hash set and look each one up. That works, but it costs a lot of memory, and if the set lives on disk, every check is a slow disk read. Now here's the insight. What if you didn't need a perfect answer? What if a data structure could tell you either, definitely not on the list, or probably on the list, using a tiny fraction of the memory? That is exactly what a Bloom filter does. And probably turns out to be good enough for a huge number of real systems. Concept 1: what a Bloom filter actually is. It's simpler than people expect, just two ingredients. A Bloom filter is two things. First, a bit array, a row of bits, all starting at 0. Let's use a small one with 12 bits for our example. Second, a set of independent hash functions, say 3 of them. Each hash function takes an element and returns a position in the bit array. That's the entire structure. No elements are ever stored, just bits. That's why it's so small. A real Bloom filter might use a few million bits to represent tens of millions of items. Concept 2: insertion. Let's add our first elements and watch the bits flip. To insert the word apple, we run it through all 3 hash functions. Say they return positions 1, 4, and 9. We simply set those 3 bits to 1. Now let's insert a second word, orange. Its 3 hashes give positions 4, 7, and 11. We set those to 1 as well. Notice position 4 was already 1, from apple. That's fine, bits are shared, and we just leave it set. After inserting apple and orange, the bits at positions 1, 4, 7, 9, and 11 are on. Everything else is still 0. Insertion is just hash and set some bits. It's big O of k, where k is the number of hash functions. Concept 3: lookup. This is where the magic, and the catch, appear. To check whether apple is in the set, we hash it again, getting positions 1, 4, and 9, and we check those bits. All 3 are 1, so we answer, apple is probably in the set. Now let's check mango. Its hashes give positions 2, 4, and 7. We look, and position 2 is 0. Because that bit was never set, apple, orange, nobody touched it, we can say with total certainty, mango is definitely not in the set. That's the key asymmetry. If any bit is 0, the answer is a definite no. If all bits are 1, the answer is only a probably yes. Concept 4: false positives, the single most important property to explain in an interview. Here's the catch. Let's check grape, an element we never inserted. Suppose grape hashes to positions 1, 7, and 11. We check the array, and all 3 are 1. But wait, we set bit 1 when we added apple, and bit 7 and 11 when we added orange. Grape itself was never inserted, yet every bit it checks is on. So the filter reports, grape is probably present. That's a false positive. Here is the guarantee to memorize. A Bloom filter can produce false positives, but never false negatives. If it says no, it's always right. If it says yes, it's usually right, but not always. In our block list example, a false positive just means you do one extra, unnecessary check against the real database. You never wrongly let a bad URL through. Concept 5, the math. You don't need to derive it, but knowing the knobs makes you sound senior. 3 numbers control a Bloom filter. M, the number of bits. N, the number of elements you'll insert. And K, the number of hash functions. The false positive rate goes up as you add more elements, and down as you add more bits. There's an optimal number of hash functions, roughly m over n, times the natural log of 2. And a handy rule of thumb, to get a 1% false positive rate, you need about 9.6 bits per element, with about 7 hash functions. So 10 million items at 1% is roughly 12 megabytes, versus hundreds of megabytes for the raw set. That space saving is the whole point. Concept 6, a crucial limitation. You cannot delete from a standard Bloom filter. Why can't you delete? Think about removing Apple. You'd want to clear its bits, positions 1, 4, and 9. But position 4 is also used by Orange. If you clear it, you'd break Orange, and a lookup for Orange would wrongly return a false negative, which the whole design forbids. So a plain Bloom filter is insert and query only. If you truly need deletion, you use a variant called a counting Bloom filter, which replaces each bit with a small counter. Insert increments the counters, delete decrements them, and a position is considered set if its counter is above 0. The cost is more memory. Concept 7, what it looks like in code. You rarely write one by hand in production, you'd use a library like Google's Guava. But the core is tiny. You hold a bit set, and to add an element you loop over your k hash functions, each returning an index, and set that bit. To check membership, you loop the same hashes, and if any bit is 0 you return false immediately, definitely not present. If all are 1, you return true, probably present. A common trick, instead of k separate hash functions, you use 2 good hashes and combine them, h1 plus I times h2, to simulate k of them cheaply. Concept 8, where Bloom filters actually run. You've used them today without knowing. Databases like Cassandra, HBase, and Google's Bigtable put a Bloom filter in front of every on-disk file, so a read can skip files that definitely don't contain the key, avoiding pointless disk reads. Content networks and caches use them to check, have we seen this item before hitting the origin? Web browsers, including Chrome's Safe Browsing, used Bloom filters to test URLs against lists of known malicious sites. And they appear in spam filters, and in avoiding recommending content a user has already seen. The pattern is always the same, a cheap probable membership check in front of an expensive exact one. Concept 9, when to reach for a Bloom filter, and when not to. Use a Bloom filter when 3 things are true. Membership testing is your question. A false positive is tolerable, because you'll do a real check afterward. And memory or speed matters enough to justify it. Do not use one when you need exact answers, when you need to retrieve the actual elements, not just test membership, or when you need deletions and can't afford a counting variant. Said simply, a Bloom filter is a fast, tiny, approximate gatekeeper in front of a slow, exact source of truth. Name a real example, like Cassandra skipping SS tables, and you'll show you truly understand it. And that's the Bloom filter, end to end. A bit array plus a few hash functions. Insert by setting bits, lookup by checking them. Never a false negative, only the occasional false positive. Tunable with M, N, and K, no deletions without a counting variant, and running quietly inside Cassandra, Chrome, and countless caches. Explain it with the example we built, apple, orange, and a great false positive, and any interviewer will see you get it. To practice out loud with mock interviews and spaced repetition, head to prepforge.net. If this helped, subscribe for more. Thanks for watching, and good luck in your interview.